Good morning. We are Valentin Arrúa and Diaz. We are here today for the presentation of our paper. It is called "The Possibilities of Using Energy Provided from Nuclear Fusion in the Near Future." In the modern world, countries are looking for change their old methods of generation energy for a new renewable methods. In this objective was stated by the United Nations, or for example appears as one of the NAE NAE grand challenges. And in this context, the nuclear fusion energy appears as a big possibility, a massive generation of energy of using this technology with any bad environmental impact. So this energy is one of the biggest investment the humanity can do for their own future. And in this paper, we are going to explore the possibilities of use this technology in the near future, of use this massive energy to power our houses and our life in the near future. And for that, first of all, we are going to talk about the historical context of the nuclear fusion energy, and after that, we are going to describe the main obstacles of creating a nuclear fusion. Then we are going to show the solutions that scientists have discovered or planned to overcome the different obstacles. After that, we are going to talk about some economic issues about the different ways of creating the nuclear fusion. Near to the end, we are going to show some projects that are working on that solutions and how they are overcoming these the possible obstacles that are appearing in the development of the reactors. And finally, we will give you a conclusion of the possibilities of use this energy in the future. Maybe what year or what projects are more near to be finished in the near future.
Well, first, with some historical context, there was an utopian idea of using nuclear fusion energy that has stayed in people's minds since the Second World War. Since the 50s, scientists and countries have been working on the first concepts about how to create commercial and useful way to produce it. One example of the power of the nuclear fusion were the famous hydrogen bombs created in 1953. And over the years, the technology grew strong enough to have some experimental prototypes in the 70s that could not work in a continuous way. In fact, they were built just to establish the structural necessities for future reactors. From the 70s until today, the advance in the creation of an effective system to generate and contain this massive power has taken only small steps.
Okay. In the next part, we are talking about the obstacles of creating a nuclear fusion. There are maybe two very important obstacles when we talk about of create this nuclear fusion. The first one is the Coulomb forces, and the second one is the confinement wall. And why? Well, the Coulomb force is the electric force between two charged particles. In this case, the fuel of a nuclear fusion is a tritium and a deuterium, that are two positive charged particles. And when you have two particles with the same charge, the Coulomb force turns into a repulsion force. So one particle tries to separate from the other particle. And this force is very big, and it's not possible to imagine how to do it with a normal way in the human world. So it's necessary to design another way to accelerate these particles to overcome this force and make the collision possible. In this context, scientists discovered that this fusion is possible to occur when it's heated at 50 million Celsius degrees. So in this temperature, these Coulomb forces turns very small. They are not important and makes possible the fusion between these two particles. And this temperature is called ignition temperature, and this process using this special method is called thermonuclear fusion or hot melt. There are other problems that is the elastic collisions, because the particles, when they collide and in a big space, they possible ricochet and don't create a fusion. So we need to reduce the space to increase the possible collisions and the possible fusions. And this reducement of the space make that the time the fusion needs to occur will reduce a lot. So this is one of the main obstacles, how to reduce the space using a material that can resist the very harsh environment that produce this fusion. In the modern world, there is no material that can resist that very hard environment because of its temperature. And when a normal material touch this plasma, turn into a radioactive waste, and this is not the idea of the fusion. So there is the needing of find a way to isolate the plasma and for the objective that it don't touch these walls.
So the plasma made in the reactor's camera needs to be isolated. Well, for this there are two current methods of generating nuclear fission, two solutions. The first one, the magnetic confinement, and the second one, the inertial confinement. The magnetic confinement is actually the most advanced and used method for obtaining fusion. It consists in using the Lorentz force, which is a magnetic force felt by a charged particle, through a magnetic field to prevent the plasma particles from touching the walls of the reactor, which could take place because of gravitational or inertial action. And in order to achieve this, the scientists have developed a device that makes this possible, the Tokamak. It is a device developed to carry out the magnetic field that will keep the plasma isolated inside the reactor. It consists in a vacuum chamber with a toroidal shape, and on the outside surface of the chamber, the conductive cables wrap up the toroid, making a coil through which an electric current passes, forming a phenomenon named Torres effect, where the magnetic field is stronger in the inside than the outside. So it allows to the particles to circulate in a spiral way without touching the Tokamak's walls. The second solution was inertial confinement. This is one of the alternatives to magnetic isolation method, since it is based on the fast generation of energy before the ignited plasma has time to expand. It is an easy way to produce fusion. Initially, there is a deuterium-tritium spherical capsule named Arrúa of few millimeters in size and at a low temperature. It is powered by a driver, which consists of a large array of lasers aimed at the fuel. This energy compresses the fuel to high densities and heats it up to the temperatures needed to create the plasma. This results in a mini nuclear explosion in the center, and the heat generated spreads outwards, heating and igniting the plasma. All this has to happen before the compressed plasma expands and cools down, which happens in less than 10 nanoseconds. If this is during this time more energy is produced than the invested, the experiment is favorable. As we can see in the picture on the screen, we can see this phenomenon. First, the radiation rapidly hits in the surface, generating plasma with the laser pulse. Secondly, by means of an action-reaction effect, the plasma expands outwards and the fuel is compressed. Thirdly, the capsule reaching a very high density and temperatures. And last, the nuclear fission takes place in the center and is transmitted to the adjacent compressed fuel, producing more energy than the one is consumed in the process.
Okay. Now it's time to talk about the economics of the nuclear fusion. The solutions to the different obstacles a nuclear fusion reactor have to overcome represents a lot of costs because it is a very new technology and it represents a very large building in terms of facilities and plants. And we are going to explain the most important issues about the economics of every kind of solution we mentioned before. And in this context, it's very important to remember the very big cost a technology like this represents.
Well, the inertial fusion energy's economic issues. The cost of inertial fusion energy electricity comes from the initial capital investment in the construction of the plant, the human resources, miscellaneous supplies and equipment, and the cost of the pellet is negligible. It's so small. But more than half of the remaining capital cost is for a single piece of equipment, the driver. The driving costs could be reduced if, for example, a single driver is used for a large number of targets, but bringing the driver down, for example, for maintenance, then the large number of targets would not produce energy. This can be easily solved by providing two separate drivers with a switch in order to alternate one as other is in maintenance. This only shows us that a way that we could improve the driver's function. Now, like we see in this graphic, there is various studies of drivers of lasers with the relation between their direct cost and the driver energy. They have almost a linear function, and we can see that the driver energy impacts in his costs. But in any case, the economics of the inertial fusion can always be improved by reducing driver costs, which also depends on driver energy, like we said. So two areas for further research are highlighted from the last condition: improving target designs and optimizing target and target chamber designs. The first one will reduce the driver's energy. One will increase capsule ignition rates, allowing lower capsule energy release and driver energy. While there are several drivers that promise high enough efficiency, it will be attractive to have an inertial fusion concept with a higher efficiency gain product and allow a smaller driver size. That concept may be the fast ignition, and nowadays it is the central objective of many of the most important projects of fusion.
Well, when we talk about the magnetic fusion energy economics, we can divide it in three parts. The first part is the construction or the building of the power plant and the facilities. It represents approximately about 73% of all the initial investment. Compared to a coal plant or a fission plant, it represents a similar percentage of the initial investment. So for an energy company, it's nearly the same to make an investment in this kind of technology or in a coal plant. And we know a coal plant it's very bad, have a very bad in the environment. The second part is the replacement of the different parts that compose the reactor. In this case, we can talk about the divertor and the blanket or first wall. And these pieces are they suffer a lot with the heat of the plasma and the energy that the fusion produce. And all the cost, the economic cost this part have very variations, because it depends a lot of the capacity of these parts of withstand the wear, and it represents about 16% of all the cost. And the last part is for the operation and maintenance costs and other costs, and it represents about an 11% of all the cost of a reactor, a nuclear fusion reactor. We can see this in the picture on the right, and on the left we can see a picture of global electricity generation in a hypothetical world where the fusion is already a useful technology. And in the first chart we can see a distribution of the electricity generation without any climate policy. And in the second chart there is a comparison of the electricity generation with a very strong climate policy. And this is the case we are going, the world is going to do, because people and countries in general are looking for more strong climate policies that lets our future generations to have the same life we have with a health environment.
Well, last, the big ally nuclear fusion has the climate policies. The countries and people have been fighting for a clean future for a long time. Nowadays, in the 21st century, environmental protection is possibly one of the most important challenges in the international scene. Fusion energy is a low-carbon system of energy production. So this method of obtaining energy will not pay special taxes, which, for example, coal energy pays. These political and economic decisions, plus the constant pressure made by the young generations, the environment protection societies, and every person that has suffered or is suffering the effects of contamination, pave the way for a friendlier ecosystem for this kind of technology. In the near future, it is possible for the costs of fusion energy to decrease the operation costs to be the same as those invested in fusion energy, making it more widely available.
Well, in this part, we are going to talk about projects working on solutions. Before we start to show them, it's necessary to explain that what is Q. Q is the fusion energy gain factor. It's a factor that represents a relation between the energy gain energy at fusion, or the energy output, with the energy input or the energy used for the reaction. And when we have a Q under the number one, we have a loss of energy. So the reactor, this hypothetical reactor, is inefficient. Well, with this, we can start to talk about the different projects.
The first project is National Ignition Facility. It is not project itself, it's just the laser, the driver that can operate many kind of projects. As we said, National Ignition Facility, or NIF, is a large laser-based inertial confinement fusion research device located at the Lawrence Livermore National Laboratory. NIF aimed to achieve fusion ignition with high or at least favorable energy gain. NIF researchers worked on the ignition of the fuel pellet inside the hull room, but they did not achieve the ignition despite all the efforts made. So the NIF officially ended on September 30 of 2012. Scientists kept investigating laser energy, pellet quantity, hull room spherical form, and other parameters in order to achieve their main objective. Also, NIF has been working since 2016 with magnetized linear inertial fusion, the MagLiF, in order to also investigate key aspects of using a single squad of NIF to deliver, for example, 30 kilojoule of energy to a target whose data return was very favorable, and analysis is ongoing by scientists and the Lawrence Livermore National Laboratory.
SPARC. The SPARC is a project created with the basis of the ITER and the others magnetic reactors, and the innovation that SPARC proposed is the construction of a compact reactor with a very big magnetic field. In this case, the radius of the reactor is 1.85 meters and the magnetic field is 12.2 Teslas. And all the tests and studies of this new project said that this reactor can achieve easily a Q equal 2. And in the near future, it will achieve a Q equal 10. So in this very happy future, all the team of the SPARC team decided to start the construction of this reactor by 2021, and these compact constructions represents less cost in construction and investment. So it's a little step for the construction of a commercial type nuclear fusion reactor, being maybe one of the most important in the near future. The next project we are going to talk about is the Fire X1. It's a Japanese inertial nuclear fusion reactor prototype. It is focused in the creation of two very large lasers The first one is the Gecko 12, and the second one is the LFEX. And all the scientists try to create a very powerful lasers, because the reactor, when the fusion starts, the harsh environment created by the plasma produce a loss of power for the lasers. So scientists are very focused in increase the power of these lasers. The least information we find about this project from 2011, 2012, the latest tests show that the efficiency of this reactor were about 20%. But nowadays there is no new information, and we don't know why. Maybe it's a policy of protection of the technology. Maybe there are no new results, or maybe this project just ended by any reason. We don't know, obviously. But maybe it's one of the largest projects we have seen when we are making an investigation of the different reactors.
The International Thermonuclear Experimental Reactor, or ITER. ITER is an international collaborative project aimed at demonstrating the scientific and technological feasibility of fusion energy for peaceful purposes. It consists of a deuterium-tritium tokamak of 24 meters of diameter and 28 meters of height, which has been designed to create a plasma of 500 thermal megajoules or megawatts for around 20 minutes, while 50 megawatts of thermal power are injected into the tokamak. It will result in a Q equal 10. The project began its 5 years assembly phase in July of 2020, being 2025 the year expected to initiate the experiments with the reactor. The programmatic objective of ITER is translated into a number of specific technical goals, all concerned with developing a viable fusion power reactor. 1. ITER should achieve at least Q major than 1, keeping the target of Q equal 10 predicted. Secondly, ITER must extend the duration of the reaction. Thirdly, ITER will implement and test the key technologies and processes needed for the future fusion power plants. And fourth, ITER will test and develop concepts for breeding tritium from lithium-containing materials inside thermally efficient high-temperature blankets surrounding the plasma. This mega project could make important contribution to the nuclear fusion world. If ITER achieves its goals, the production at a commercial scale of nuclear fusion energy will be very close to become a reality. In the last project we will talk about is Wendelstein 7X or W7X. W7X is the world's largest fusion device of the Stellarator type at the Max Planck Institute for Plasma Physics. The Stellarator is a new form of tokamak devices, shaping the best geometric way to take advantage of magnetic fields. Wendelstein's objective is to investigate the suitability of this type for a power plant. It uses magnetic confinement, and the device will test an optimized magnetic field for confining the plasma. The project consists of 3 operations. One successfully concluded in 2016, and 2 are keeping ongoing. The only disadvantage is that the Stellarator has particular environmental conditions to operate. It is too specific. but until today it seems to not be a problem yet. Beyond that, Stellarator optimization is also a current research which scientists at Max Planck Institute are working on. In conclusion, this paper has finally shown at least 4 different types of nuclear fusion designs. It started with the simple magnetic and inertial confinement nuclear fusion devices, showing their economic and physical issues. Since then, many other kind of devices have emerged, like Wendelstein 7X, whose fundamental working is a combination with magnetics principle, but a different Tokamak device, the Stellarator in this case, which is much better. Also, there are projects not mentioned as examples in these papers, like TIA, which works with the field reverse configuration principle, or ITER, which works with magnetized target fusion, the hybrid combination between magnetic and inertial confinement method. It means that there are multiple configurations for a nuclear fusion plant design, and there could be more in the future, that will be more effective than the older ones, because that is the way science and progress works. Many of the projects mentioned above are going to be finished in 5, 10, or 15 years, and maybe their goals could not be achieved before 2045, but it is not a reason for giving up. It is a fact that there is a very high possibility for commercial nuclear fusion to be giving energy to the world before the end of the century. It is just a question of work and time. Thank you very much for listening.
Thank you very much.